Good evening, class, and welcome to week 4 of Living Systems 1. Tonight we're going to look at lecture 4, covalent compounds. So we're following on from last week where we talked about ionic compounds, which are formed from one major type of bond in chemistry. And tonight we're going to look at the second major type of bond, covalent bonding. And in reality, particularly for everyone here tonight and for myself, these are the compounds, the covalent compounds that we come into contact the most, particularly in biological systems, whether they are animals or plants or even bacteria, for that matter. So we had a question before I started the recording. What is this on the front slide here, this image here? And I'm going to come back to this later because I'm sure that by the time we've completed this lecture, you will know exactly what this is. That is, you'll know what each of these coloured spheres are, and more importantly, you'll understand the nature of the bonds, these bond lines in between each of the coloured spheres, which of course, as you know, represent different atoms of different elements. And you'll also understand a little bit about the shape, the molecular shape of covalent compounds, that is their geometry. Okay, so let's look at covalent bonding. Covalent bonds result from the sharing of electrons between two atoms. And of course, you'll remember from last week that ionic bonds result from the transfer of electrons between atoms. So this is quite different here, and we're going to go through some examples, starting here with an atom of hydrogen. And you can see here the single valence electron that hydrogen contains. Here we have another atom of hydrogen, also with its single valence electron. But before we look at the bonding, I'd just like to illustrate something about hydrogen. So hydrogen on the periodic table has the number 1 above it. Number 1. What does this number, the atomic number, tell us about hydrogen? Who remembers?
The amount of protons.
Number of protons, yes. And also the number of what in a neutral atom of hydrogen?
Electrons.
Electrons, correct. So number of protons and also the number of electrons in a neutral atom of hydrogen. Now, what about the number below hydrogen? 1.0 something. 1.01. Yes, mass number. We can refer to this number as the mass number. And remember, we can also refer to that number as the atomic mass. But we won't worry about atomic mass for now. Let's just think about it in terms of mass number, because we can use the mass number and the atomic number to tell us how many protons, electrons, and neutrons are found in one atom of hydrogen. And remember how we do this? We write the element symbol for hydrogen, and we place the mass number up here, rounded. So we're going to just round that to 1. Here's the mass number, placed as a superscript, and then the atomic number, which is also 1, as a subscript. Okay, so with this particular representation of an atom of any element, we can actually calculate the number of protons, electrons, and neutrons. So, how many protons do we have in hydrogen? According to one proton, 1 electron. Now, who remembers how to work out the number of neutrons using those numbers? How do we work out the number of neutrons?
D minus the mass
atomic mass from the number of protons or electrons?
Yeah. We actually take away this number, the atomic number, subtract that from the mass number. And so what do we get there if we do that?
0.
0. So there we have it. Hydrogen actually lacks neutrons. One hydrogen atom has 1 proton and 1 electron. Most hydrogen anyway, okay? The most abundant isotope of hydrogen, this is how it's actually found. All right, keep that in mind for another day, that hydrogen is one of those unusual atoms that actually lacks neutrons. And I'll just clear all that before we go on. All right, so let's go back to our covalent bonding and sharing of electrons. Here's our 2 hydrogens, each with its single electron, which is also its valence electron. Now let's consider the electron configuration for hydrogen, and you'll know that that's simply 1s1, which of course means that hydrogen's electron is in the first shell, S subshell, and there's the 1 electron. Now you can see that this is not a completely filled shell or completely filled subshell. So what hydrogen tends to do very readily is to form a bond, a covalent bond with another hydrogen atom. And we can see that here. So the 2 hydrogens have actually come together and each one is contributing an electron to this bond that's formed in between them. In other words, we can write it like this: hydrogen with its 1 valence electron, a second atom of hydrogen with its 1 valence electron, and the sharing of those 2 electrons between them, and that's not a very straight line, the sharing of those two electrons between them means that the hydrogen on the left is now surrounded by 2 valence electrons, and the hydrogen on the right is also surrounded by 2 valence electrons. So what this results in is almost an electron configuration of 1s2. In other words, the most stable arrangement for hydrogen, because it now has that filled S subshell. Okay, so we don't actually rewrite the electron configuration the way I have there. This is just to illustrate that hydrogen in this form, in the form of a diatomic molecule, that is 2 atoms in the 1 molecule, is more stable than each hydrogen atom on its own. And that's why hydrogen in the atmosphere is normally found as H2. 2 hydrogen atoms bonded together as a result of the sharing of electrons between 2 atoms. Okay, let me clear that and get rid of the pen. All right, we can also see here that as a result of that bonding between the 2 hydrogens, that each hydrogen nucleus now has 2 electrons, that is 2 electrons surrounding each of those 2 hydrogens, and this gives it the noble gas configuration of helium. And helium is particularly stable because it has that 1s2 electronic configuration. So a covalent bond is simply a 2 electron bond in which the participating atoms actually share the electrons between themselves. And a molecule is a discrete group of atoms held together by covalent bonds. So normally we would use the word compound when we're talking about the formation of a substance as a result of ionic bonds, but when it involves covalent bonds, we normally refer to that substance as a molecule. But as I've said before, those terms often are used interchangeably. So let's look at another example. We've got hydrogen once again, and with its one valence electron. And here we have fluorine. Now, just to make sure that everyone remembers, how would you determine the number of valence electrons that a particular atom has? What rule do we use for the main group elements?
Group number.
Group number, good. Okay, so we know hydrogen belongs to group 1A on the periodic table, and there's its one valence electron. Fluorine belongs to which group on the periodic table?
7A.
7A, correct. Fluorine belongs to 7A, and what are the 7A elements referred to as? What are they called?
Halogens.
Halogens, very good. I want you to remember that, halogens. That's why I keep repeating it. All right, so 7A, so fluorine has 7 valence electrons, and of course that's illustrated here for you with this electron dot symbol for fluorine. Now, think about this again. Hydrogen with 1, it actually wants 2 to fill that 1s subshell. Fluorine has 7. How many does fluorine want to be stable?
8.
8, yes. So remember 8, the octet rule. Fluorine wants 8 electrons. So what happens? Fluorine and the fluorine and hydrogen will readily combine, as you can see here. And these 2 electrons in the centre, one of those comes from the hydrogen, one comes from the fluorine. So if we look back here, look at this single electron here to the left of fluorine. That's the one that's going to participate in this sharing, in this covalent bond that forms between the 2. So I'll just get my pen once more. Okay, now let's look at what's happened as a result of this covalent bond. How many electrons are surrounding the hydrogen? We actually, 2, there we go. So we actually select both of those electrons that are participating in the formation of the covalent bond. We can say that hydrogen is now surrounded by 2 electrons, so it's filled its 1s subshell. What about fluorine? How many electrons are surrounding the fluorine atom?
8.
Everyone can see that? 8. So it started with 7, now it's surrounded by that octet of 8 electrons. So both of these atoms are now more stable energetically. Let's look at that covalent bond once again. Here we can see those 2 electrons are indicated by a solid line in between the hydrogen and the fluorine. That solid line is how we normally denote a covalent bond. So from now on, when you start seeing these solid lines in between atoms, think about that as a 2 electron covalent bond. And I'll just clear this drawing. Okay, let's note another important feature here. Fluorine, we can see 2 electrons up here that don't participate in any bonding, well, not in this case anyway. Another 2 electrons there and 2 at the bottom. So what we have here are lone pairs. We call them lone pairs because they're not currently participating in any bonding. And we refer to the number of these non-bonded electrons as 3 lone pairs of electrons. So keep that in mind for some of you tutorial questions now and in the future. 3 lone pairs of electrons or 3 non-bonded electron pairs. All right, so remember hydrogen will only share 2 electrons, that is 1 of its own and then 1 from another atom. Other main group elements tend to be stable when they possess an octet of electrons in their outer shell. So just some general rules that we can apply. All right, now I'm going to, if you don't mind, there's a little bit of feedback coming from someone's mic, and I'm just going to check out who the culprit is. All right, that's better. Okay, sorry guys, I had to put you on mute, but feel free to unmute yourself at any time. There was just a lot of background noise. Okay, any questions so far?
No.
No? All good?
Yeah.
All right, let's move on. I'll just clear that. All right, on this slide, we're going to look at what are referred to as Lewis structures. These are simply electron dot structures, the same as what you did last week, but these are electron dot structures for entire molecules. So let's see how that works. Here's our first example, methane. Let's look at the formula for methane, it's CH4. A Lewis structure will actually show us exactly how these atoms are connected to each other. It'll show us the location of the covalent bonds in between these different atoms and any lone pairs of electrons if they're present in the molecule. So let's draw this. Carbon belongs to which group on the periodic table?
4A.
4A, so it has 4 valence electrons. Let's draw those 4 valence electrons around carbon. How many electrons does carbon want to be stable? How many do you think? Applying our rule.
It's got 6.
It's got 4 valence electrons.
Oh, 4. Right.
4 valence electrons because it belongs to group 4A, but it actually wants 8, an octet of 8 to be stable. So if we take each of these hydrogens in CH4, and of course each hydrogen has a single valence electron, I hope you can see all them clearly, and now draw in our covalent bonds between them. And now as a result of these 4 covalent bonds, we can actually see that carbon is now surrounded by 8 electrons. So carbon has achieved its octet, and of course each of the hydrogens is surrounded by the ideal 2 electrons to achieve a more stable configuration. Now that's a bit messy, but we can see it also here, the way that it's drawn here. So we can see hydrogen, each hydrogen is surrounded by 2 valence electrons, and I won't indicate that for each of the hydrogens, but just as importantly, the carbon, that central carbon, is surrounded by 8 electrons rather than just 4. How is that drawn? We can see in this representation here that each of those covalent bonds are simply indicated by these solid lines. So remember, each of these lines indicates the presence of 2 electrons within the covalent bond. Let's try another example of a Lewis structure, and this example is ammonia, which has the formula NH3. So how is that nitrogen and the 3 hydrogens connected to each other? All right, firstly, we need to know how many valence electrons nitrogen has. So nitrogen is found in group 5A on the periodic table. Yep. So we will go 1, 2, 3, 4, 5 valence electrons for nitrogen. Sorry, they're not very clear. Okay, nitrogen has 5. How many electrons does it want? to be stable? It only has
8.
5, 8. It wants 8, exactly. Always think of that octet rule. Well, for most of the elements that we deal with anyway. It wants 8. Now we can see that there are 3 hydrogens in ammonia. So let's place them around nitrogen. Here we go. And you know that each hydrogen has a single valence electron. There they are. And now we can draw in the bond lines. From there, there, and there. So 3 bonds, 3 covalent bonds. Let's look at the result of that. How many electrons are now surrounding nitrogen?
8.
8, exactly right. So nitrogen has fulfilled the octet rule, and of course each of the hydrogens is happy because they are surrounded each by 2 electrons. Now looking at that nitrogen there within ammonia, can anyone see, sorry, I'll just clear this. Can anyone see here any lone pairs of electrons?
The 2 up the top.
2 up the top, but how many lone pairs do we say nitrogen has, ammonia has, rather?
1.
1, okay, so just note that, everyone. These 2 electrons here are not participating in the formation of any covalent bonds, so we say there is 1 lone pair of electrons here in ammonia. Let's try one more example, water. And here's the formula for water, H2O. Let's draw this, the Lewis structure. Oxygen belongs to group 6A. So how many valence electrons does oxygen have?
6.
6, correct. 1, 2, 3, 4, 5, and 6. All right, how many does it want? How many electrons? 8. It wants 8, yes. So it needs to pick up, this oxygen needs to pick up 2 additional electrons. And it does that very easily from 2 hydrogen atoms. Let's draw them in. And not that it's actually gaining those electrons, but it's actually sharing them with hydrogen. Okay, here's our 2 covalent bond lines. And now we can see, as a result of the 2 covalent bonds between oxygen and 2 hydrogens, how many electrons is oxygen now surrounded by?
8.
8, correct. Oxygen has fulfilled the octet rule, and each of the hydrogens is happy because they are surrounded by 2 electrons. And we have our lone pairs of electrons also. How many lone pairs does a molecule of water have? Just
2.
looking at, yep, 2 lone pairs, correct? Here we go, let's look at them. So these 2 electrons and these 2 do not participate in the forming of covalent bonds. Okay, good. Just clear that. Okay, so when you're confronted with different substances, how do you tell, just by looking at them and using the periodic table, whether it's an ionic compound or whether it's a covalent molecule or covalent compound? All right, who remembers what elements or what groups of elements tend to form ionic compounds? Who remembers
Metal
that?
and a non-metal.
Sorry?
A metal and a non-metal.
Correct. So ionic compounds tend to form between a metal and a non-metal on the periodic table. Covalent bonds tend to form when 2 non-metals combine or when a metal bonds to a non-metal. Okay, so that's a really useful rule to remember there. So how do we determine how many covalent bonds a particular atom will form? Another couple of rules that you can follow here. And remember these rules, there's always exceptions to these rules, as you've already learned. So atoms with 1, 2 or 3 valence electrons generally form 1, 2 or 3 covalent bonds respectively. And we saw that with hydrogen, for example. It has 1 valence electron, it tends to form 1 covalent bond. Atoms with 4 or more valence electrons will form enough bonds to achieve that octet, that is those 8 electrons. And we've also seen some examples. So one example was carbon. Carbon has 4 valence electrons. So in order to form enough bonds to give that carbon an octet, it will form 4 covalent bonds. Predicted number of bonds simply equals 8. Take away the number of valence electrons a particular atom has. All right, so this is a really nice table which illustrates the number of bonds formed by the most commonly encountered atoms in covalent bonding. So we've already seen hydrogen, which, all right, we've got some noise in the background again. Who can I mute? Try this one. That's better. All right, sorry, I had to mute someone there. It was a lot of background again. All right, so we've already seen hydrogen, which has 1 valence electron and it forms only 1 covalent bond. And of course, it doesn't have any lone pairs of electrons. Carbon, we've seen that carbon belonging to group 4A on the periodic table has 4 valence electrons. It wants 8. So in order to achieve 8, the octet of 8 electrons, it will form 4 covalent bonds. And that's illustrated here around the carbon atom. Nitrogen, we've also seen, nitrogen belongs to group 5A, which gives it 5 valence electrons. It wants 8. In order to achieve that, it will form 3 covalent bonds. In other words, it will use 3 of its 5 valence electrons to participate in the formation of 3 covalent bonds. So nitrogen, 3 covalent bonds, and that leaves it with 1 lone pair of electrons. Oxygen we've seen as an example. All right, sorry, we've just got, can't see the PowerPoint side that you're on. Oh, that's interesting. Okay, someone can't see the PowerPoint.
Are you on number 6?
Yeah. Yes, I'm on oxygen.
All right, it's changed back. Cool.
Okay, can you see it now, Emily?
Yep.
Yep, okay. Oh, so you weren't actually seeing this slide. Is that what you were saying?
Yeah, I was seeing number 6.
Oh, right, okay. So there was a bit of a lag time in changing of the slide.
Yeah.
All right, thanks for letting me know. All right, so oxygen, as we said, belongs to group 6A. That gives it 6 valence electrons. It wants 8. In other words, it will form or use 2 of its 6 valence electrons to form 2 covalent bonds, thereby giving it that octet of electrons. So oxygen will form 2 covalent bonds, and that leaves it with 2 lone pairs of electrons. Okay, the halogens. Group 7A, fluorine, chlorine, bromine, iodine. They possess 7 valence electrons. They want 8. In other words, they will form, use 1 of their 7 valence electrons to form 1 covalent bond. Here it is here, 1 bond, and that leaves the halogen with 3 lone pairs of electrons, as you can see here. All right, any questions so far? And we've got people.
Yeah.
We've got people coming in and dropping out. I don't know if that's because of internet connections. Yeah, sorry, someone's got a question.
Is astatine still a halogen?
Sorry?
Astatine?
No.
No, it's not.
It's not. No. If you
Okay.
look back at your periodic table when we actually labelled the metalloids, the metals and non-metals.
Yeah.
Okay, so just look back at that, and that'll answer your question. Okay.
Yeah.
All right, so we've just looked at what Lewis structures are, and keep in mind that a simple molecular formula, such as H2O or CH4 and so on, will show the number of atoms in a compound, the identity of the atoms in a compound, but it doesn't actually indicate which atoms are bonded to each other and how they're bonded to each other. A Lewis structure, as we've just seen, shows how those atoms are connected to each other, as well as the location of all the bonding and non-bonding valence electrons. General rules for drawing Lewis structures: draw only the valence electrons, give every main group element, except of course the hydrogen, an octet of electrons, and give each hydrogen only a maximum of 2 electrons. All right, let's go through the steps that you would use to draw a Lewis structure. And I promise you won't be tested on this, but it's very useful to know how to do this. Step 1, arrange the atoms next to each other that you think are bonded together. Place hydrogen, any hydrogens, and any halogens on the periphery, since they only ever form the one bond. So for this example, CH4, we've got 1 carbon. Of course, we'll place carbon in the centre and the hydrogens around the outside. This arrangement of the atoms is incorrect. One reason is given here, because if we arrange the hydrogens in this way, this indicates that this hydrogen is forming a bond to the carbon and also a bond to this hydrogen on the right. And you know that's wrong because hydrogen will only form one bond. There's one more problem with this particular arrangement of atoms. Who can pick it? Who can see what the problem is? And I'll give you a clue, it involves the carbon.
That would be a single paired electron.
Yes, correct. So if we had carbon only being surrounded by 3 hydrogens, and the bird's going a bit crazy in the background, that indicates a covalent bond there, 1 there and 1 there. Where would the other, what would the other one of carbon's 4 electrons be doing, basically? It would be on its own down here. More importantly, how many electrons would be surrounding the carbon? Would it be surrounded, in other words, by an octet?
No.
No, it wouldn't, because there would be 2 electrons there in that bond, 2 there, 2 there for a total of 6, 1 down here for a total of 7. So carbon would not achieve that favourable octet arrangement. Step 2, count the valence electrons. So for main group elements, you know that the number of valence electrons is equal to the group number, and this will give the total number of electrons that should be used in the Lewis structure. Here's another example, CH3Cl. Let's look at each of the atoms and how many valence electrons is associated with each. So we've got a single carbon here. 1 carbon has 4 valence electrons for a total of 4. 3 hydrogens, each one has 1 valence electron for a total of 3. And then 1 chlorine, Remember that one's a halogen in group 7A, so it has 7 valence electrons. This gives us a total of 14 valence electrons that need to be placed. Arrange the electrons around the atoms, place one bond, that is one covalent bond, each one equaling 2 electrons between every 2 atoms. For main group elements, make sure that that octet rule of 8 electrons has been satisfied. And of course, for hydrogen, don't give them any more than 2 electrons. Use all remaining electrons to fill octets with lone pairs, beginning with atoms on the periphery. All right, for CH3Cl, again, we place carbon in the centre. Remember, carbon nearly always forms 4 covalent bonds. I think someone in class referred to carbon as the party animal of the atomic world. All right, we've got our hydrogens on the outside and our halogen also on the periphery here. 2 electrons only for each hydrogen in the form of these covalent bonds. And we've got our 3 lone pairs here on the chlorine. So if we were to count all those up, we can say 4 covalent bonds are found in this Lewis structure for a total of 8 electrons, 3 lone pairs on the halogen, that is the chlorine. Each one consists of 2 electrons for a total of 6, and we have used up all our 14 valence electrons. All right, now what we've been looking at so far are single covalent bonds. Single covalent bonds, that is just one solid line which contains 2 electrons. Single covalent bonds. But there are lots of examples of, of molecules that consist of multiple covalent bonds. The most common ones that we encounter are double covalent bonds and triple covalent bonds. Let's look at why these are required, why they're necessary in some molecules. Okay, we're going to look at this example of a diatomic molecule, that is 2 atoms in the one molecule, oxygen. So oxygen is generally found like that in the atmosphere, 2 oxygen atoms bonded together. Let's draw this, oxygen and another oxygen. Each one has 6 valence electrons. Draw it like this and like this, and 6 here. Okay, let's look at what would happen if there was only a single covalent bond in between those oxygens. Single covalent bond. In other words, how many electrons are surrounding this oxygen to the left?
7.
7, only 7. Yep, let's count them. 2, 3, 5, 6, 7. Okay, that's a problem. Only 7 valence electrons surrounding that oxygen, and of course, the same applies to the second oxygen. Only 7 valence electrons. Remember, those oxygens prefer to achieve the octet rule, 8 electrons. So let's try that again. Clear that. Now what happens? 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Once again, now what happens if we put 2 covalent bonds in between the oxygens. How many electrons now are surrounding the oxygen to the left?
It has 8.
And now has 8, correct. So if we count all those electrons in there, you can see 2, 4, 6, 7, 8. And the same applies to the other oxygen 8 electrons. So you can see why oxygen is particularly stable when the two atoms are joined by 2 covalent bonds. Let's now do the same thing with nitrogen, diatomic nitrogen, molecular nitrogen, N2, or you might wish to call it atmospheric nitrogen. That's how it's normally found. Nitrogen, group 5A, which means each atom has 1, 2, 3, 4, 5 valence electrons. 1, 2, 3, 4, 5. All right, let's try molecular nitrogen with a single covalent bond. How many electrons are surrounding that nitrogen to the left? 2, 3, 4, 5, 6. So the octet rule has not been achieved there, and not for the other nitrogen. All right, let's try that with 2 covalent bonds. That is a double covalent bond. Two, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now how many electrons are surrounding each of the nitrogens? 1, 2,
7.
7. 2, 4, 5, 6, 7. Correct. So we've got 7 electrons surrounding each nitrogen. Once again, octet rule has not been achieved. All right, that brings us to our triple covalent bond. A triple bond contains 6 electrons contained within 3 covalent bonds, as you can see here. All right, now let's count the electrons surrounding each of the nitrogens. Let's look at the nitrogen to the left, and we can count 3, 6, 8. So the octet has been achieved for that nitrogen, and the same applies to the nitrogen on the right. Can everyone see that? How the octet rule has been achieved now for each of the nitrogens, and hence why the triple covalent bond is found here.
Yeah.
Yes? Good. All right, is everyone else clear with that?
Yep.
Yes? Terrific. Hey, Chris. All right, so let's look at how multiple bonds are drawn in Lewis structures. Example, draw the Lewis structure for C2H4. The carbons are arranged in the center once again, and the 4 hydrogens on the outside. The valence electrons are counted, 2 carbons, each with 4 valence electrons for a total of 8. 4 hydrogens, each with 1 valence electron for a total of 4. This gives us 12 valence electrons in total to place. Now, using this particular arrangement here and drawing in a covalent bond line in between each of the atoms, results in the placement of a lone pair of electrons here, which is incorrect because carbon here still does not have an octet of electrons. And as you know, carbons tend to form 4 covalent bonds, not 3 as shown here. Okay, in order to give both of those carbons an octet, 2 electrons that are left over are actually used to form an additional bond line in between the carbons. We can see that here, a double bond between those 2 carbons, and now each carbon has its octet and all the electrons have been used in this particular Lewis structure. Once again, that was only for your interest. All right, as we've said many times, there are exceptions to all these rules, unless, of course, you're a physicist. I don't believe that there's exceptions to their rules. Most of the common elements generally follow the octet rule. We know that hydrogen is an exception because it only needs 2 electrons to fill the 1s subshell. Elements in group 3A don't actually have enough valence electrons to form an octet in a neutral molecule. So you can see this example here, which involves a group 3A element, and it is only surrounded by 6 electrons. Some more notable exceptions. Elements in the 3rd period on the periodic table have empty d orbitals, which are available to accept electrons. That means that some of these elements may have more than an octet of electrons around them. 2 good examples here. Phosphorus, in this particular example, is surrounded by 10 electrons, and sulfur, in this particular molecule, is surrounded by 12 electrons. All right, now we're going to revisit one of our polyatomic ions from last week. Does anyone remember what the difference is between a polyatomic ion and an ionic compound? So if you can't remember the polyatomic ions, that they were found within a table on the last slide of last week's lecture. The polyatomic ions, how do they differ from ionic compounds? So remember that table had examples such as carbonate, bicarbonate, sulfate, nitrite, nitrate, and so on. Sorry, someone's got an answer for me.
Is it just a different, like, configuration?
Sorry, can you say that again?
Is it just a different configuration?
A different configuration? Yeah, you could say that. I'm looking for more specific details. So in particular, if you remember, an ionic compound results from that electrostatic interaction between 2 oppositely charged species. That's not the case for polyatomic ions.
So it's not an ionic bond, and it has
Exactly right. Yes.
It has 2 different charges.
And it carries a charge, yes. So polyatomic ions firstly consist of more than 1 atom. Secondly, those atoms are bonded together, not by ionic bonds, but by covalent bonds. And number 3, as someone just mentioned, a polyatomic ion carries an overall charge. That's not the case for a balanced ionic compound. Let's just revisit this just briefly. Never hurts to go over these concepts. Remember that we said sodium as an ion carries a single positive charge. And chlorine as an ion carries a single negative charge. Everyone remembers that? So we're talking about charged species that are just single atoms. When they're single atoms, they are charged as a result of gaining or losing one or more electrons. But what happens when they actually come together in the forming of an ionic bond? When they actually form that ionic bond as a result of that attraction between those opposite charges, what happens to the overall charge now on this ionic compound? What is the overall charge on this now?
Zero.
Zero, exactly right. The overall charge now is zero. So ionic compounds, when we balance them in this way, so one positive for every negative, the overall charge is zero. But polyatomic ions, and we can see an example here, this is the cyanide ion, still carries an overall charge. Okay. In an ionic compound, the bond between the atoms is an ionic bond. In a polyatomic ion, the bonds between the atoms, in this case, it's a triple bond. These are covalent bonds. Okay, not ionic bonds. All right, so that's just a little bit of a refresher for you. And we're going to look, as I said, at the polyatomic ion cyanide, Cn with a single negative charge. Let's start by looking at the atoms and their valence electrons. 1 carbon, 4 valence electrons for a total of 4. 1 nitrogen, 5 electrons for a total of 5. And then, of course, we have a single negative charge. Does that mean that this particular polyatomic ion has gained or lost an electron? Bit more revision here. It's gained an electron, correct. So when we see a negative charge, in this case a single negative charge, this means that there is an additional electron present. So that's 1 additional electron, and so we have a total of 10 valence electrons to place here. Well, 9 valence electrons plus 1 extra. All right, so let's look at carbon and nitrogen with just a single covalent bond between them. Does this work? That means that carbon is surrounded by how many electrons? How many valence electrons? Only 4, so it's lacking that octet. What about nitrogen? I'll just clear. Nitrogen is surrounded by 2, 4, 6, 8, surrounded by 8. But that's incorrect anyway, because nitrogen would not have 2, 4, 6, 7 valence electrons. Nitrogen only has 5 valence electrons. So that's all wrong. Completely wrong. Clear the drawing. Let's look at the correct Lewis structure for cyanide. We have carbon, now surrounded by 3, 6, 8 electrons. So carbon has achieved its octet, and nitrogen also surrounded by an octet. Here's the additional, this indicates that there's an additional electron present within that Lewis structure, which is essential in order for both nitrogen and carbon to achieve those octets of electrons. And that's why cyanide tends to scavenge that additional electron from its environment in order to achieve this particular compound, where the octet rules have been satisfied for both of those participating atoms. Okay, so as an exercise, you could actually look at drawing this representation of cyanide, but with only using carbon's 4 valence electrons and nitrogen's 5 valence electrons. You would see that it would not work without this additional 1 valence electron.
Where do they
Okay.
get that from?
Sorry?
Where do they get the extra electron from?
Good question. Where does the extra electron come from? Who would like to try to answer that question? Where might the additional electron come from?
A metal that has a spare?
Yes, yeah, basically. So when we're talking about metals in the environment that will readily lose electrons, and you can probably think of some examples of these from last week, metals will readily lose electrons to any other substances in their immediate environment because they tend to be more stable once they've actually lost that electron. Yep. And you'll understand more about this when we come to a later lecture where we talk about a particular class of chemical reactions, which shows how some elements tend to very readily give off electrons and others tend to gain or scavenge those electrons. Good question. Okay, naming covalent compounds. Who remembers their naming rules for the ionic compounds? And who remembers that I said last week that ionic compounds are named very differently to covalent molecules? Does anyone recall that?
Is that just the endings with the IT and all that?
The endings, yes. So in ionic, when we're naming ionic compounds, we tend to use different suffixes, yes, and that's also the case for covalent molecules as well. So you might not recall, but for ionic compounds, when we name them, we don't specify the number of atoms in that compound within the name itself. We don't specify that in the name, but with covalent compounds we do. This is one of the major differences between the two. And of course, it's also one reason why it's useful to be able to identify an ionic compound when you see it and distinguish that from a covalent compound, because there's two slightly different sets of rules used for naming them. All right, so let's look at how this is done for covalent compounds. Firstly, name NO2 and N2O4. So both with nitrogen, both with oxygen. We name the first non-metal by its normal element name and the second using the suffix "ide." So let's name them. Nitrogen is simply nitrogen. And then oxygen, we use the suffix "ide", so oxygen becomes oxide. What about our second example, N2O4? We name this nitrogen, and oxygen becomes oxide. So you can see the problem here already. We have the same names, but two very different molecules in NO2 and N2O4. So obviously we need to specify within the name how many nitrogens and how many oxygens are found in these two very different molecules. Very simple to do. We simply add prefixes to show the number of atoms of each element. The prefixes are found on the following slide in table 4.1. We'll look at that in just a moment. If you need to use the prefix mono, indicating only one atom of a particular element, you can normally just leave that out. One exception to that rule is CO, carbon monoxide. So in the name of this particular molecule, we actually specify that there is a single oxygen there. And of course, you can imagine why, because carbon monoxide has to be distinguished from carbon dioxide, which is CO2. All right, if the combination of words within the name places two vowels next to each other, then omit the first vowel. For example, if you had to use the prefix mono and the element name oxide, then we have the two vowels here, the two O's next to each other, but rather than naming this monoxide, drop one of these O's, and that gives you simply monoxide. All right, here's the table, which shows the common prefixes used in naming covalent molecules. Number one atom, one particular atom, is the prefix mono, which we don't normally use. If there's two atoms of a particular element, we use the prefix di. 3 atoms, tri, 4, tetra, and so on. Okay, so I'd like you to remember up to number 4. Okay, so note that you should remember these prefixes up to number 4 for the purpose of tests and exams and so on. All right, so let's go back to our 2 examples. NO2, so the N, of course, we can just call that nitrogen. We don't have to say mononitrogen. And we have 2 oxygens in this particular molecule, so we use the prefix di, and the name becomes nitrogen dioxide. Our second example contains 2 nitrogens, so we need to specify that in the name, use the prefix dinitrogen. 4 oxygens, what prefix do we use? Here it is, 4, we use tetra. Tetraoxide, no, because that contains the 2 vowels next to each other, the A from tetra and the O from oxide. So drop the A from tetra and the name simply becomes dinitrogen tetroxide, not dinitrogen tetraoxide. All right, moving on from naming covalent molecules, and now we're going to look a little bit at how to determine the molecular shape of a given compound, a given covalent molecule. That is, what do we know about the geometry of these molecules? The geometry is actually predicted by this theory called the valence shell electron pair repulsion theory, or simply VSEPR. And this theory proposes that the most stable shape or geometry for a given molecule is determined by the repulsion between neighbouring electrons. That is, the electrons within a particular molecule will try to stay as far away from each other as possible, and that's what determines molecular shape. All right, so to determine the shape around a given atom, first determine how many groups surround the particular atom. We'll look at what those groups are, some examples. A group is defined as either an atom or a lone pair of electrons. Then we use the VSEPR theory to determine the shape. As we just said, the most stable arrangement for a given molecule will keep those groups as far away from each other as possible. Remembering that like charges will repel each other, and hence why those negatively charged electrons try to stay as far away as possible from each other. All right, so let's look at what happens when there are 2 groups surrounding a specific atom. Here's an example. Here's the atom in question in red, and here are the 2 groups surrounding it. In other words, 2 atoms surrounding that central atom. Okay, an atom surrounded by only 2 groups will form a linear shape. The molecule will take on a linear shape with bond angles of 180 degrees. So we can see this is a linear molecule. Here's an example, an actual example, which is carbon dioxide, CO2. Here's the atom in question, the carbon. Here are the two oxygens. So we say that this carbon is surrounded by two groups. In this example, two atoms. The geometry is linear. And the bond angles are shown here, 180-degree bond angles. All right, what happens when we're looking at a molecule that has three groups surrounding an atom? Here's our central atom in question, and we can see the three groups. In this case, once again, three atoms represent the three groups. The bond angles are 120 degrees, and the molecule will have the trigonal planar geometry. Here's an example here, H2CO. This is formaldehyde. Central carbon, where are the three groups? 1, 2, and 3 groups surrounding that carbon. Here we can see the 120-degree bond angles, and here we have the geometry, trigonal planar molecule. So when we say it's a planar molecule, that means it's flat, basically has a flat shape. All right, another example, 4 groups surrounding an atom. An atom surrounded by 4 groups is tetrahedral in shape, and it has bond angles of 109.5 degrees. Once again, here's our central atom and the 4 groups, or 4 atoms in this case, surrounding it. Now, this answers someone's question that we had right at the beginning. What was that structure that you saw on the very first slide of this lecture? And here it is right here. What you were seeing was the molecular shape of one atom of methane. Methane has this chemical formula, CH4, and what you are seeing is the central carbon and the 4 hydrogens represented by these blue spheres. You now know what these solid lines represent. What do these solid lines represent in terms of bonding? What have we been learning about tonight?
Single covalent bond.
Single covalent bonds, exactly right. Now you know when you see the solid line, these are single covalent bonds. What you haven't actually seen so far is what this dashed line represents, and this solid wedge line here. They also indicate single covalent bonds, but they tell us a bit more about the actual geometry, the 3-dimensional shape of this molecule. Let's look at it down here. So here's the dashed line here, and this represents, or this indicates, that that particular covalent bond is situated behind the plane of the carbon. This dark, this bold wedge here, again, this is also a single covalent bond, but it's telling us that this particular hydrogen is positioned in front of the plane of that carbon, and therefore that forms our tetrahedral molecule. All right, once again, we have 4 groups around an atom, but if the 4 groups in question includes 1 lone pair, then the geometry is a little bit different. So keep this in mind, that the groups surrounding an atom can be other atoms, or they can be lone pairs of electrons. If there's 1 lone pair included in those 4 groups, then the geometry is said to be trigonal pyramid, and the bond angles are a bit sharper at 107 degrees. An example is NH3. This is ammonia. Let's look at ammonia down here in terms of this Lewis structure. Here's the nitrogen, 3 bonds to 3 hydrogens, and a remaining lone pair of electrons, which forms the fourth group surrounding the nitrogen. This is how we can picture it. The nitrogen with its 3 hydrogens, so there's 3 groups, and here's the fourth group here, the lone pair. So, yes, do we have a question?
Yeah, Silvana, so is it fair to kind of say if there's a lone pair, the repulsion from the lone pair is greater than the repulsion from each other, so that's why it bends?
Absolutely correct, and keep in mind that the lone pair has to be considered a group. The lone pair has to be on the actual central atom. So if we have lone pairs on the other groups, then they don't count as groups within themselves, if that makes sense.
Okay, yeah, thanks.
Okay. All right, so we can still think of this as a tetrahedron, but when we look at this, the molecular shape here, we can see that it's a very compressed version of a tetrahedron, if you like, and it's referred to as the trigonal pyramidal molecule. Okay, and one more example, I think. If the 4 groups around the atom include 2 lone pairs, then the geometry is still that of a tetrahedron, but the molecular shape is more accurately described as being bent. So once again, we have that compression of the tetrahedron, and the bond angle's a little bit sharper again at 105 degrees. Classic example of a bent molecule is water, H2O. Let's look at the Lewis structure. Here's our oxygen, 2 covalent bonds. So we've got 2 groups represented by the 2 hydrogen atoms, but now we've got the 2 lone pairs of electrons on the oxygen also being considered as groups. Here's a good representation of water, the oxygen here, the 2 hydrogens, and here we have the lone pairs. And an example of the bent molecule, which represents water. All right, our final concept in this lecture tonight, and a very, very important one at that. So this is something that I want everyone to really get their head around, and a very important one in terms of revising and revising again until it's all really clear in your mind. This is the concept of electronegativity. It's very important. It comes up again and again in future lectures, and it's also something that's really important to understand so that you can appreciate the rules of solubility once we come to those lectures. Right, electronegativity. Let's define this term. Electronegativity is a measure of an atom's attraction for electrons in a covalent bond. So let's just try to visualize this. Try to visualize this firstly by thinking about just a single covalent bond between these 2 atoms. So here's our single covalent bond, and let's put in the electrons that are participating in this bond. Okay, so the way that I've drawn these electrons, you can probably imagine that they're being equally shared between atom A and atom B. But what if I was to draw that a little bit differently? What if I drew it like this? Okay, what is that telling us? The way that I've drawn those 2 electrons in that covalent bond, what is that telling us? Sorry?
That B wants the electron more than A.
Exactly right. You can see here that B has a greater pull on those 2 electrons in that covalent bond. So that means that B has a higher electronegativity than atom A. That is, it exerts a greater pull on those 2 electrons. Now, what if I... What if I drew... Sorry, we have a question?
But does A still keep that electron?
Yes, it does. Yes, very good question. So even though B is exerting a greater pull on the 2 electrons in the covalent bond, it does not mean that B actually takes this electron from A. That's a very, very important point, and I'll come back to that in just a minute. Very good point. All right, in this example, we can see the 2 electrons over here. So that tells us that atom A, in this case, has a greater electronegativity than B. Okay, and we can draw it in all sorts of ways, just so you can visualise this concept of electronegativity. So we might have it there, we might have an electron being pulled a little bit towards B, but not a great deal, and so on. All right, electronegativity values. Let's look at them as we can see them here in this table. Now, these values that you can see are not shown on your version of the periodic table. You would actually have to source this information elsewhere. We can see that fluorine has a very high electronegativity value of 4. In fact, fluorine has the highest electronegativity value out of all these elements shown here. Oxygen, a little bit lower, but still very high at 3.5. Let's look at some examples here. Sodium has a very low electronegativity value. What about carbon? This is a very common one. Carbon has a lower electronegativity value, 2.5. Nitrogen, 3, and so on. Okay, so keep these electronegativity values in mind for some of your tutorial questions, and also we're going to come back to some of these values in just a minute. All right, let's look at an example of electronegativities of 2 bonded atoms. So here we have 2 carbon atoms, and you can see the covalent bond in between them. The electronegativity value for carbon, as seen on that table on the previous slide, is 2.5. If the 2 atoms that are participating in the covalent bond have the same electronegativity values, or as you can see in this example, they have very similar electronegativity values. For example, 2.5 here for carbon. Hydrogen has a value of 2.1. We say that they are quite similar in terms of the pull that they would exert on the electrons in those covalent bonds. Okay, so when the electronegativities are equal or very similar, we say that that covalent bond is non-polar. It's a non-polar covalent bond. That might not make sense at the moment, just bear with me. Okay, and what this actually tells us is that the electrons in those covalent bonds shown there are being more or less shared equally between the 2 atoms. In other words, carbon, carbon, we have an equal sharing. Carbon, hydrogen, more or less equal sharing, okay, of those electrons in those covalent bonds. Oh, I've just gone the wrong way. All right, now let's look at an example where there is a greater electronegativity difference between the atoms in that covalent bond. So we've got an example here, shown here, carbon, oxygen. Let's just go back, have a look at the electronegativity values for carbon and oxygen. Carbon 2.5, oxygen 3.5. In this example, carbon, oxygen. Oxygen has a value of 3.5. Carbon has an electronegativity value of 2.5. That tells us that oxygen has a greater pull on those electrons in that covalent bond. That is, the electrons in the bond are unequally shared between the carbon and the oxygen. Now remember, each electron that we can see here has a negative charge. So if you have an additional negative charge in the vicinity of this oxygen, this actually confers a very slight partial negative charge to the oxygen because of the close vicinity of that additional electron, that additional negative charge. The carbon, on the other hand, the carbon is almost, but not quite losing that electron, which confers a partial positive charge to the carbon. Okay, so these are not your positive and negative charges that we see in ionic species. So for example, Na plus and Cl with a negative charge. These are very slight partial charges. And we refer to these charges in this one here. This one here is referred to as delta negative. And this one here is referred to as delta positive. So think of those as very, very just partial charges exerted on the carbon and the oxygen as a result of the unequal distribution of electrons in that covalent bond. All right, as a result of the partial positive and the partial negative charge being imparted on the carbon and oxygen, this sets up what is known as a dipole. Here's the word here, a dipole. Who can explain what that means in really simple terms, or even give me an example of a dipole that you would just commonly encounter? Something that you would just commonly encounter that has opposite poles.
A magnet?
A magnet, yeah. What else?
A battery?
A battery, yes. Excellent example. Yes, opposite poles, different poles, positive and a negative. That's the best way to think about this term, a dipole. And that's what we have here, a dipole. And this is also referred to as a polar covalent bond. So bonding between atoms with different electronegativities, so significantly different electronegativities, which we saw here in terms of the difference between the carbon with a 2.5 and the oxygen with an electronegativity value of 3.5 has resulted in the creation of a dipole, that is the positive, delta negative, and we now refer to this particular covalent bond as a polar covalent bond, or simply as a dipole. All right, let's just recap again. Electrons are pulled towards the oxygen in this example. Oxygen is the more electronegative element. That is, it has the higher electronegativity value, and this is indicated by the symbol delta negative. Electrons are pulled away from the carbon, and remember, carbon doesn't actually lose its electron. Electrons are pulled away from the carbon, which is the less electronegative element, with a value of only 2.5, and this is indicated by the symbol delta positive. Okay, that brings us up to our last slide of this lecture. Electronegativity difference and bond type. So, if you see an electronegativity difference between two atoms participating in a covalent bond, and that difference is less than 0.5. And we saw an example of carbon and hydrogen. 2.5, 2.1, the difference between those two is less than 0.5 units. When you see this, the covalent bond type is non-polar, which means the electrons are equally shared and we don't have the creation of a dipole. When the electronegativity difference between the two atoms is between 0.5 and 1.9, and we just saw that on the previous slide, the difference between carbon and oxygen. The bond type is a polar covalent bond, or you can say that it's that we've created a dipole, and that means the electrons are unequally shared. They are pulled towards the more electronegative element. If the electronegativity difference was greater than 1.9 units, let's look at what happens. This is where the electrons, rather than still being shared within that covalent bond, they're actually transferred from the less electronegative element to the more electronegative element. In this situation, we would no longer have a covalent bond. Instead, we would have an ionic bond. And that completes our lecture for this evening. Who has questions?
I have one, Savannah.
Yes.
I noticed that the chemical, the formula for ammonia and methane.
Yes.
Started with carbon or nitrogen, but then water started with the hydrogen atom.
Yeah, that's
like a.
Is there some system? There probably is. There probably is. Yeah, that's a really good point. And I think it's actually something that you raised last week too. Okay, so here, we've got the CH4. So starting with the carbon here, starting with the nitrogen, but here we start with the hydrogen. Yeah, so you're asking, is there a system to determine how we start these formulas?
Yeah, I guess if you're a bond and you want to write the chemical formula for it, how do you which element goes first?
Which one goes first? Yeah, that's a good question. Yeah, I'm sorry, I can't answer that at this moment.
Okay.
Yeah, there's probably a system in place. There are probably rules that determine that. I think in my case, certainly, you just get so used to the way that the atoms are presented within compounds and molecules. Yeah.
Okay.
Yeah. No, that's a good question. Certainly one that we can look into. Any other questions on anything that we've learnt tonight? So now you should be able to complete all the tutorial questions in the tutorial set on ionic bonding and covalent bonding. Remember that they are not assessed, but they're still very, very important because, of course, those questions are still preparing you for the mid-semester test, the final exam, and so on. So make sure that you still go through all those questions, check your answers by submitting your answers through the online quiz. And of course, that particular quiz is not assessed. You can have multiple attempts at the quiz because it's not assessed. And then let me know if there's still any of those questions that you're not sure of. Let me know before next week, particularly before we move on to the next topics. All right, so any questions?
Silvana, I noticed some of the questions in that quiz are where you have to write an answer. Will we let you know that we've done them so that you can correct them, or how does that work?
Yeah, absolutely. So you'll notice, have you actually gone through the online quiz yet?
Half of it. So I did the ionic bonding.
Okay, yeah. When you come up to a question like that, you'll notice that you're instructed in the online quiz to either draw it, and some students are able to draw that somehow, or you can just describe how you would draw it. So, for example, if you had to draw an electron dot symbol, you could simply provide as your answer that the electron dot symbol for carbon would be a C surrounded by 4 dots, which represents the 4 valence electrons. Does that make sense?
Yeah, and then but you can't sort of get the answer to those. You don't know if you're wrong or right on those immediately.
No, not immediately. No, you would have to wait. For questions like that, you have to wait for me to actually go in manually, which I do, and I correct them manually and give feedback on them.
Okay, so you do that. Yeah. We don't need to let you know that it's in there waiting.
Oh, no, you don't need to let me know. What I normally do with, and you might have noticed that already, well, some of you might have noticed that for the tutorial questions on elements and the periodic table. One of those questions, you had to state a group number, and then actually list the elements found in that particular group. Yep. So for those students, so obviously you had to actually type in that answer. And for those students that didn't get that quite right, I actually provided feedback in the form of a comment. So for example, students might have included all the elements in group 1A as well as hydrogen, not remembering that hydrogen is the exception to the metals rule. Okay, so that feedback is provided manually by me at the end of that quiz period.
Perfect, thanks.
Yeah. Okay, no problem. All right, who needs a break before we go on to talk about prac reports? Would anyone like a 5-minute break to clear your heads?
Yes.
Yes. All right, I'll give you 5 minutes, or would you like 10 minutes?
5.
5. All right, let's have a 5-minute break, and then we're going to come back and start talking about how to write a formal scientific prac report. Okay, I'll see you in 5 minutes. Hello, I'm back.
Hello.
Hello.
Yep.
All right. What we can see here is the prac manual. Some of you won't have seen this yet, but I'm going to put a copy of this on Moodle. So those students that are doing the 2-day workshop can start working your way through the pracs before you get to the weekend workshop. Now, I should mention something really important here. Students are always told to read the prac before they go to prac class. This is common practice. It's really important, but it's also a source of some stress and frustration for students. And I understand completely why, because you'll read the prac and you come to the end of the prac, and then how many of you think, I don't understand what I just read? Is that a common? That's very common. Yeah, common. It's normal. Don't expect to read any of the pracs and understand everything you're reading. This is something that takes time. It takes practice. It takes time. It takes years to actually master being able to read a protocol and really understand what you're reading. And even then, often it takes you to actually carry out the protocol to really understand it in its entirety. So let me make that clear. When you read a prac and you think to yourself, I don't understand anything or very little of what I just read, that's normal. Okay, but it is important to practice. It's important to keep that practice going, because you will be confronted with protocols regardless of your major, whether it's a new water testing protocol for aquaculture students, it could be a new soil testing protocol or soil preparation procedure, plant tissue testing procedure. You will have to know how to follow protocols. So really important part of your training to be work ready. Viticulture and winemaking students, you'll have to follow protocols for various types of testing that you do. Testing of wine, so testing for sulfur levels, testing for levels of different sugars, testing for alcohol, and so on. Okay, this all involves protocols. So regardless of your major, and keep in mind, don't be discouraged when you read pracs and you don't really understand what you're reading. As long as you know what the aim is, and just have a general idea of how you're going to be conducting a particular protocol. Okay, and don't think about it in this way. Students often say, but I don't want to work in a lab. That's not why I'm doing this course. I don't want to be working in a lab when I'm finished. And of course you don't want to be working in a lab, well, most of you anyway. You want to be working on agricultural businesses, for example, or for vineyards and so on. But the labs are what we use to demonstrate and carry out these protocols. That's what we have at our disposal. All right, so let's go right through this prac manual right to the end, or close to the end, and you'll find some important information on writing prac reports. Now, some students will never have written a formal scientific prac report, and they're not too bad once you know what's expected. So let's have a look at, here we go. So we're on page 78 of the prac manual, and this is where the information starts regarding prac reports. All right, so part of the assessment for living systems requires you to submit 2 500-word prac reports based on 2 different pracs. Submission dates, we've already gone through this. This is also on Moodle. These dates are also on Moodle and in the subject outline for Living Systems 1. So make sure that you take note of the submission dates. They're a little bit different for weekly prac students versus 2-day prac workshop students. All right, some information here on formatting, style, and just one important point here about style. Avoid writing in the first person or in the second person. In other words, don't use words like I or you or we or they. Write in the third person and use past tense. Remember that you're writing about a prac that you've already completed. Okay, so you're writing in past tense. All right, the word limit. This is an important point here. The word limit is 500 words, but the 500 words is only counted from 2 sections of your report. That is from the introduction and aim section and also from the discussion conclusion section. In other words, the text that you write in your materials and methods, in your results, in your reflection, and in your reference list is not included in that word limit. So I normally recommend that students try to write about 250 words in their introduction and aim section and aim for about 250 words in your discussion conclusion section. Okay, so keep that one in mind. All right, here are the sections that you must include in your report. So of course you'll have a title. You can use the same title that's provided for that particular prac that you're writing on, or you can come up with your own title if you like. Then we have the first section, introduction and aims. Once again, aim for about 250 words here. Materials and methods section, results, discussion and conclusion. Once again, aim for about 250 words here. Then you'll write a brief reflection only for one particular report. So you must write a report on the acid-base prac. That's one report. The other report, you can choose any prac. Any prac that you do, you can select one prac and write a report on that prac. And then you'll have a final reference section. All right, let's go through a little bit of information on each section. So we'll start with the introduction and aims. Now, the introduction section should start with a short background to current knowledge of the topic or the problem under investigation. So, in other words, don't start by saying the aim of this prac is to. Don't start with that. The aim always comes at the end of the introduction, not at the beginning. Start off by giving me some information from the literature about the particular topic. So, for example, when you're writing the acid-base prac, start off by defining acids and bases. What are acids and bases? What are some examples of acids and bases? Then that leads into the problem or what's being investigated, and then you finish with the aim, the specific aim. So with an introduction, you always start with that very general information, and then as you proceed through that intro section, you become more and more specific. You must use references to provide this information in your introduction. Therefore, you must include in-text references for the information, and these in-text references will let me know whether you source that information from a textbook, from a journal article, from a particular website, and so on. Now, I only ask that you don't use Wikipedia as a reference. Not that there's anything wrong with Wikipedia. Don't get me wrong, Wikipedia is terrific. But the reason you can't use it as a reference is that that information is more or less taken from other sites, other references. And you can scroll to the bottom of a particular Wikipedia page and look at where that information has actually come from. And they are the references that you can use, not the Wikipedia site itself. Okay, so keep that in mind. Also make sure that you're very clear on what type of references you should be using for any assessment in any of your subjects. Some lecturers are very particular about the types of references that they want you to use. So for example, they might say the only websites that you can use are government websites, university websites, and so on. Other lecturers might say the only references that I want to see are references to scientific journal articles. So always clarify that with your individual lecturers in different subjects. As I said, I don't mind which references you use as long as you're not directly referencing Wikipedia. All right, materials and methods. Just briefly on this section. Materials and methods, you won't be listing in a separate list the materials required for that particular prac. Instead, those materials are incorporated into your description of the methodology. The methods are written out almost the same as you'll find it in the prac manual, but with the difference. In the prac manual, you're given a list of instructions. You're told what to do to carry out that particular protocol. But when you're writing that up in your report, you're describing what you have already done. In other words, you're writing it in past tense. So for example, if a protocol says dispense 2 ml of sodium hydroxide into a beaker, that's giving you an instruction, isn't it? Just like a recipe. But when you actually write that in your materials and methods, you will write, for example, 2 ml of sodium hydroxide was dispensed into a 20 ml beaker. Okay, so past tense, you're describing what has already been done and you're describing it in the third person. For example, you're not saying I dispensed, you are saying 10 ml of sodium hydroxide was dispensed. All right, so that's materials and methods. Results. Now the results consists of 2 parts. It starts with some descriptive text. This is how you always start the results. Don't just dive straight into a table or a graph or some other type of figure. Always start with at least a paragraph, even if it's a short paragraph, which actually describes trends or significant features in your data. So in other words, what were your main findings? State your main findings first and then present the evidence in the form of tables or figures or drawings and so on. Okay? Make sure you don't actually discuss the results, not in this section, not in the results section. Save that for your discussion. Just state what the results were, what were the findings. All right, tables and figures have to be labelled properly. In other words, label each figure and each table, depending on the prac that you write up on, with a caption which tells the reader what's been shown. For example, if you're presenting a table, then the table caption, as you can see here, goes above the table. An example here, table 1, a comparison of prokaryotic and eukaryotic cells. All right, so make sure you don't just say table 1. Also give me a brief description, give the reader a brief description of the type of information they can find within that table. All right, what about a figure? Okay. All right. Drawings and graphs are all referred to as figures. So they would be labelled, for example, as figure 1 or figure 2, depending on how many figures you have, and that's followed by a brief description. Figure captions are always placed below the figure, not above the figure. So if you present a graph as part of your results, it's not referred to as graph 1, it's referred to as figure 1, and that figure caption is placed below the actual graph. All right, that's explained here. Tables should be labelled above, figures should be labelled below. Then we have our second last section, discussion and conclusion. So this is where you analyse your results. Pay particular attention to interpreting each of your results in turn in a logical sequence, and if you can compare your results to something that's in the literature, you will get bonus marks for that. This is really good practice to say that this is what the results were, and this corresponds or does not correspond to such and such, which is in the literature. So, for example, which is in your textbook, or to something that you found online. If it doesn't correspond, try to explain, try to give some sort of explanation as to why it might not respond. Is there something that you may have done incorrectly in the actual course of that particular prac, and so on. Okay, and there's some further descriptions there of what you can include in your discussion. Usually the most difficult part of any prac report is the discussion, because you really have to think about what your results mean, analyse, interpret those results. And finally, a reference section. So this section will list the collection of references that you've used. Those references may be in the discussion, and they should definitely be in your introduction. I normally expect to see at least 3 different references within your report. And these may all be in the intro, or you may have 2 or 3 in the intro and 1 or more in the discussion. All right, so make sure you use a reference, you include a reference list. And here we have some further information on referencing and also paraphrasing, how to avoid plagiarism. So make sure you read through this information before you actually start on your lab reports. All right, if you've never used referencing before, you can refer to the Student Guide to Harvard Referencing. It's called ERNIE. This is an easy referencing tool, and it's available on our library website. This is a really easy to use tool. It basically enables you to select the type of reference you're using, whether it's a website or a textbook, and then depending on the number of authors, or maybe on whether there's a date of publication or no date of publication, it will actually give you an example of how you should present that reference, the correct way to present the reference, both in your reference list and within the text of your writing, within the text of your report. All right, and there's some examples shown here, but make sure you refer to ERNIE referencing tool. All right, I'm only also going to place a couple of examples of scientific prac reports on Moodle. They might already be on there actually, but I'll double check that, and if they're not there, I'll actually put them up for you so you can actually see an example of a formal scientific prac report. That'll give you a really good idea of what to expect and what you're aiming for. Okay, any questions on writing prac reports?
Not from me, Savan.
Not from you? Any questions from anyone else?
No.
No?
I think maybe once I start writing it, I'll have more questions.
Yes, absolutely. And keep in mind, everyone, too, if you can get your prac report done fairly early, that is at least 1 week before submission date, feel free to email that to me as a draft. And I'm more than happy to check that for you and give you some early feedback so that you can improve on that report before submitting it on the due date. All right, so keep that in mind. More than happy to correct report drafts for you, but you must get them to me early. If you send it to me the day before it's due, most likely I won't have time to actually give you feedback. So aim for at least 1 week ahead of the due date if you want feedback there. Yes, to me.
Do you do the final marking or do you do it with the lab?
Yes, I do the final marking.
Okay, so the lab tech doesn't mark them?
No.
Okay.
No, I normally do all the marking of prac reports.
Yeah.
Although I might actually get the lab demonstrator to help me. That would be terrific. Yeah. Especially at the end of semester when a flood of prac reports come in. Because in that last week of semester, on the Monday, weekly prac students submit their second report. And then on the Friday in that final week, the 2-day prac workshop students submit both of their reports. So that's a lot of marking to do. So hopefully I can get help with that one day.
Silvana, on the actual pracs we submit, and I'll be doing the weekend intensive.
Yes.
Are you able to give guidance as to, like, depending on our major, which ones would be better or more relevant?
Absolutely, yes. There are pracs, and let me go back again. There are pracs that are very, very popular with specific majors. And I can actually go through that now with you if you like. I can tell you exactly which ones. Oh, here we go. All right, here is the prac here, acid-base titration. Everyone has to write up this prac. Okay. Now this one is very popular, determination of concentration using a standard curve. I don't think this is popular for a particular major as such, and no more relevant for one major, you know, in comparison to another one, but it just seems to be very popular. Whether it's a prac that makes sense to many students, or it seems to be an easy one to write up, I'm still not too sure about that one. All right, this prac here, which is delivered in 2 parts to weekly students, enzymology part 1 and enzymology part 2. This one is very, very popular with viticulture and winemaking students. It's also very popular with agronomy students as well. So that's one to consider, enzymology.
Do you do them, like if you did the prac for that,
yeah,
would you do part 1 as a whole report, or do you do them like together as one?
Yeah, no. If you were to write up the enzymology prac, you should write up both parts as the one report.
As the one report.
Yeah. So it is the one prac, but because it's such a long prac, I've split that in the past across 2 weeks.
Yeah.
Okay, so you would write that as the one report. So that one's really popular. This one here, prokaryotic and eukaryotic cells, also one prac but split over 2 weeks. This is also a popular prac for all students. Relevant and popular regardless of major. Now, this one here, cell membranes, this is a really important prac in terms of concepts that are particularly relevant to anyone that's working with plants or animals, in fact, both. But it doesn't tend to be a prac that students write up very often because I think some of the concepts are difficult. But having said that, it is a really important prac because many of the concepts that you take away from this prac and from the relevant lecture, which will be delivered in a few weeks' time, will also come up again in other subjects in the future. So I always recommend that students have a go at writing this report, but not many students attempt it. But that's a good one to keep in mind. Yeah, so hopefully that helps answer your question.
Yeah, thanks, Alana. That's useful.
Okay, that's all right. And you'll see in Living Systems 2, we start to become a lot more specific in the pracs that are being run. So we'll have pracs that are very, very useful for, say, agriculture and agronomy students. We have a prac that's incredibly useful for aquaculture students. And then we'll have pracs that are really relevant to viticulture and winemaking students. So, as I said, that will become really obvious in Living Systems 2 in second semester. Okay. Any other questions? No, I think we're all good. Okay, don't forget the dates for the prac workshop. Those of you that are doing the weekend workshop. Yeah, the occasional student in the past has missed the prac workshop. They've forgotten. And that's really unfortunate because we cannot repeat the prac workshop just for 1 or 2 students. So please make sure, and I'll give you lots of reminders through Moodle, but make sure you've got that really penciled in very well and very clearly. Okay, also remember that we have a mid-semester exam. So that'll be at the end of week 8. And this will be an online exam based only on weeks 1 to 5 of semester. Okay, not one to worry about. Students generally do quite well, being an open book online exam. But keep in mind, don't expect to be able to do the exam without any revision whatsoever. It takes time to look back through your notes if you need to be looking at your notes for every question. You won't get through it if you have to do that. So, of course, have your notes with you, but make sure you've also revised really well for this online exam. Okay, any other questions for me? No, I think we're done then for tonight.
Thank you, Silvana.
Okay.
All right.
Thanks, Alana.
Time to go. Thank you, everyone, and I will see you all next week.
See ya.
Yeah.
Okay, bye-bye.
Bye.